All right, so let's talk about power. Complex power, apparent power, real power, reactive power, power factor. We're even gonna talk a little bit about power factor, although we covered power factor in other in earlier modules. We're gonna talk about a little bit about power factor too, as it relates to the power quantities that we're going to learn how to derive and calculate. So a lot of talk about power. All right, so the first thing I want to talk about is real power. So real power is P. This is the symbol for power, and it's measured in watts. So real power is is known as active power or average power. Resistive loads are what consumes real power. So let me back up. So in your textbook is going to refer to real power as the average power, but just know they're one and the same. Um, some people call it active power, and that's because this is the work that is actually doing the work. All right, so overall, real power is the power that is applied to an actual load to do work. It could be used to power a light, turn a motor, charge an electric vehicle, etc. You know, pretty much whenever you turn something on or see something light up, that's the actual real power doing the work. All right, so to calculate real power, you can use the following formula. So you should be fairly familiar with um these formulas as it, as they were introduced in DC. Whenever we was talking about DC circuit analysis, the only difference is we're throwing in this cosine of theta, and pretty much this is your power factor right here. Cosine of theta is your power factor, and the reason why we have to have that because we're in AC and we're dealing with power factors. All right. In DC, everything was all in phase, and so therefore you didn't really have to worry about the power factor. But whenever we start to introduce AC and reactive reactants, capacitive reactants, and inductive reactants, then and the current starts to lag and lead the voltage, then we have to start incorporating our power factor. And so make note of these vertical lines right here that are indicating that this value right here is the magnitude. So majority of the time in this section we're going to be working in polar. So the magnitude is the number that's in front of the angle symbol. All right. So these are a couple different ways you can calculate the power, and just know that this phase angle right here is equal to your phase of your voltage minus your phase of your current. And so for resistive loads, it's equal to 0. So this term right here, this cosine theta for resistive loads only, will cancel out. And you'll just be left with just the V and I, the magnitudes of your voltage times the magnitude of your current. All right, so whenever you look at the graph of real power, so let's take this graph for example. So you got one dash line. Let me see. So this dash line right here represents your voltage. This dash line that's below it represents your current. So as you can see, the current is in phase with the voltage and vice versa. So therefore you have a resistive circuit right here, or a resistive element, because in phase the current is not lagging or leading. And how I know that is because the voltage is reaching its maximum peak. At the same time, the current is reaching its maximum peak. So they are in phase. And so if you take the instantaneous power, you just take a snapshot. Let's say, for example, you take a snapshot right here, and you multiply the current times the voltage, you'll get this value right here as it relates to the power. And each time you multiply these two values together, even when it goes negative, because now you're going to have a negative voltage times a negative current, which is a positive value. So therefore, your power always stays positive. And so everything's positive whenever you are dealing with average power. All right, so reactive power. So reactive power can be inductive or capacitive. And this is measured in VARs. So this is a new unit of measurement right here, VARs. All right, so to calculate the reactive power, you can use the following formula, which is similar to the power formulas. So the main difference is now instead of cosine, you have sine of theta. And instead of R, you have X of L or X of C, depending on if it's inductive or capacitive. And again, the same thing with the phase angle. Theta V minus theta I will give you your phase angle. All right, so let's look at this graph right here. So you have your voltage, which is out of phase by 90 degrees. All right, so this is inductive. So the current is going to lag the voltage by 90 degrees. Okay. And so therefore, whenever you start to plot the power by multiplying the voltage times the current, as you can see, you start to get some energy that is going to be returned back to the circuit. So therefore, uh, inductive your inductive circuit, your inductive elements are not really is not delivering any average power, and so the average power in an inductive load is equal to zero. And likewise for your capacitive circuit, as you can see, now your current is leading your voltage by 90 degrees. And the same thing happens when you take the average of what's being returned and what's being absorbed, you come out with zero average power. So average power for a capacitive or inductive load is equal to zero. And hence that's where we introduce the term imaginary power, in which that's what these two elements are delivering or receiving, is imaginary power. So for your inductive loads, that is going to be receiving reactive power. The opposite for your capacitive loads is going to be delivering or supplying reactive power back to the system. That may sound a little confusing right now, but as we progress throughout this lecture, it'll start to make a little bit more sense. Or actually, whenever we get to the next part, which is power factor correction, you'll start to get a better understanding of how the capacitive load is supplying reactive power back to the system. All right, so here's an example. So it says calculate the average power and reactive power of the following circuit. So this is a simple circuit. You got a series of inductor with a resistor. All right, so if we calculate the total the total impedance. We get 5.39 at an angle of 68.2. And so therefore we can calculate the total current by dividing the voltage by the total impedance. And so therefore we get 2.31 at an angle of negative 68.2. Now, quick check. This is an inductive circuit. So therefore we're looking for the current to lag the voltage. The voltage at this time right here is at 0 degrees. So therefore the current needs to be behind it and needs to lag it. And that's exactly what it's doing right here. It's lagging the voltage by 68.2 degrees. And so therefore we can use our power equation to calculate the power, which these are magnitudes. And we get the following values for P, which is 10.7 megawatts, and for your inductive reactive power, we get 26.75 megavars. All right, so that's how we do a simple example like this. All right, so for complex power. So complex power is a combination of real and reactive power. So in power systems or network, we typically see complex power expressed in polar form. However, expressing the complex power in rectangular form is very helpful as well, because you can see the numerically how much real and reactive power that is contributing to that complex power. All right, so to calculate complex power, you use the following formula. So S equals V times I conjugate. This is new right here. V times I conjugate. This conjugate term right here. This is new. All that means is you're just taking the inverse of the current angle. So for example, if I equals 40 at an angle of 75 degrees, the conjugate will be 40 at an angle of negative 75 degrees. That's all you're doing. You're just flipping the sign. All right. And so likewise, S equals P plus Q. So that's your real or average power plus your reactive power. So when you combine these two guys together, P and Q, you get your complex power. And so this is in rectangular form, and you can convert it to polar and vice versa. So here's an example. You got a 12.47 kilovolts at an angle of 10 degrees. Source supplies 50 amps at an angle of negative 25. So before I go any further, I mean, you should be able to look at this and tell me whether or not if the load that this source is supplying is inductive, mostly inductive, or capacitive as it relates to the reactive power. So right here, you see the voltage is at 10 degrees and the current is at negative 25 degrees. So the current is lagging behind the voltage. But in this case, it's not 25 degrees. It's a negative 35 degrees. So therefore, this load is mostly inductive because the current is lagging the voltage. But let's continue on. All right, so it says calculate the complex power, the real power, and the reactive power. So you can simply just come over here and just take the terms, use our complex power equation. With this is one of my favorites, and one of my favorite equations, S equals V times I conjugate. And once you multiply this out, you get 623.5 at an angle of 35 degrees kilovolts amps. This is a new unit of measurement right here. So volts amps. That's what complex power is measured in, volts amps. All right, so to find the real and reactive power, all we have to do is just convert the complex power, which is currently right now in polar, to rectangular. I recommend you just plug and chug into your calculator, let the calculator do the work. And so therefore, if you break it out, you get 510.74 kilowatts plus 357.62 kilovars. And so therefore, the real part is going to be your average power, and the imaginary part is going to be your reactive power. Just like so. So you can break it out just like this. And so that's why I like this equation so much, because if you can get to your complex power, I mean, you can solve a lot of different things. You can solve for your real and your reactive power. You can solve for your apparent power. We haven't talked about that yet, but you can solve for your apparent power, and also you can calculate your power factor, which leads into our next type of power, which is apparent power. So apparent power is simply the magnitude of the complex power. So we go back up here to this example. The parent power would be this value right here. That's your parent power. All right, so notice how complex and apparent power both have the symbol of S. The only difference is that the complex power has both the magnitude and the phase angle. And apparent power only has the magnitude. So don't get those two confused. Sometimes you'll see apparent power denoted as S with these vertical bars to indicate the difference. And that's what I plan on doing throughout this module, is indicating apparent power as S with the vertical bars. In your textbook, and this is one thing I don't like about the textbook, is that it doesn't give a clear indication of apparent power versus complex power. They both use S for both, and there is a difference between the two. Um, your parent power is, like I said before, the parent power is the magnitude of your complex power. And the complex power has a combination of your real and your reactive power together. All right, so to calculate the parent power, you can use the following formula. You can use Pythagorean theorem, which is p squared plus q squared, the square root of both of those, or you can multiply the magnitudes of your voltage and your current. You can multiply the magnitude of your current squared times your impedance, or you can take the magnitude of your voltage squared divided by the magnitude of your impedance. And so here's another good relationship that you're going to want to remember, is your power factor is simply your real power divided by your apparent power. So when you think about it, your power is a percentage of your power factor is the percentage of active power that that is in your apparent power. So ideally, you want your power, your average power to be as close as possible to your reactive power. So therefore, your power factor will equal 1, which is unity. But that's not always the case. Majority of the time. All right, so right here it says calculate the parent power and power factor of the circuit below. All right, so this is stemming from one of the examples above. We already knew the active power, the average power, and we know the reactive power. And so therefore we can use our parent power formula. Or, you can just plug this into your calculator and just have your calculator do the work and convert it to complex power and just take the magnitude of your complex power, and that's going to be your parent power. And so therefore, if we take the power factor, which is P divided by your apparent power, you get 0.37. And this is a lagging power factor because it's inductive. You have mostly inductive reactive power or inductive loads. And so when you compare this to your impedance right here that we calculated, so if you take the cosine, like what we learned before in earlier modules, if you take the cosine of the angle of your total impedance, so if you do that right now, take the cosine of 68.2, you would get the same value, which is 0.37. All right, so now let's talk about adding power. And I'm talking about adding apparent power, complex power, real, reactive, all types of power. And so regardless if the load is in series, parallel, the average power, reactive power, and complex power is additive. So you can just add them all up together. It doesn't matter if they're in series, parallel, whatever you have, whatever type of configuration. If you know the power of that particular load, you can add it together with your other loads, respectively, to it, whether or not if it's. You have to add like terms, so you can't add your average power from one load to your reactive power from another load. You still have to add them together separately, but regardless of whether or not if they're in series or parallel, you can just add them together. And in the following example, you'll see what I'm talking about. So the only thing that you can't add together like that is your apparent power. It is not additive without knowing more information about it. And the reason being is because that apparent power can be at a different angle. And if you just only have your apparent power, if you just only know your apparent power, and if they don't have it, if the apparent powers that you're adding together doesn't have the same angle, you're going to get the wrong value. So you have to know the angle that is associated with that apparent power, to which if you know that, then you know the complex power, which goes back to this first bullet. So if you know the complex power, you can just add them all together. So this example right here will kind of go into more details on how to add power. It's kind of a long example. So make sure you got your calculator ready to follow along with me. So right here it says determine the power factor, average power, reactive power, complex power, total current, total impedance, and and the components of each load. And then I tell you also the frequency is equal to 60 hertz. So right here we have a series parallel network. And so the loads are given to you. So right here, load 1 is 150 watts. Load 2 is 125 watts and 100 VARs, which is capacitive. That's what that that's what the C stands for. And load 3 is 75 watts and 900 VARs inductive. And then you have 100 volts at 90-degree angle for your source voltage. And so, like I said, regardless of whether or not these are in series or parallel, you can just add them together. So for our P total, we can add all our average powers together. So we have this is supposed to be 150. So we can add 150. This is supposed to be 125, and this is 75. So all right, so I got them fixed. So your total power, you can just add them together. So all your P from load 1, load 2, and load 3. So 150 plus 125 plus 75 will equal 350 watts. All right. And then now you can add your reactive power, which is your QL1 plus QL2 and your QL3. So do we have any reactive power in load 1? No. So it's 0 VARs. And so what about this guy right here? So this is going to be negative. So you're going to be subtracting 100 VARs. And then this is adding 900 VARs, which equals 800 VARs. And so now you have your total power and your total reactive power. And so therefore, if you combine them together, you get your complex power, which is 350 watts plus 800 VARs, and you express this in polar form, which would be 873.21 at an angle of 66.37 volts amps. All right, so therefore, and if you take the magnitude of your complex power, you get your apparent power, which is this number right here, this value right here. And so now we can just simply just take our power divided by our apparent power and calculate our power factor. And at the same time, if we take the cosine of our complex power angle, we can also calculate the power factor. So there's a lot of different ways you can calculate this power factor. You can use the magnitudes, the angles of your voltage and current. You can use the angle of your impedance. Now you can use your average power and apparent power, and also you can use the angle, take the cosine of the angle of your complex power. So a lot of different ways you can calculate the power factor. And so this one calculates to be 0.40. Is it lagging or leading? It's the question. Well, because you have a positive angle and your reactive power is also positive, this is a lagging power factor. All right, so let's find the total current. So we're going to go back to our complex power equation. So if we manipulate the equation to solve for I, like we've done below, we can calculate the total current. And so you start off with S equals V times I conjugate. Just go ahead and manipulate that equation to solve for I conjugate. And so to get rid of this conjugate, you take the conjugate of both sides, right? And then you have it, and it reduces to I equals S over V. And then you take the conjugate of that part. And so if we just plug and chug, you get your total complex power divided by your volts. And don't forget to take the conjugate. That's one thing a lot of people forget to do. Take that conjugate, which is just simply just reversing the angle. And so you get 8.73 at an angle of 23.63 degrees amps. All right, so let's find the total impedance. So here's a note. So don't forget to take that conjugate. So find the total impedance. So reverting back to the complex power equation again. This is why I love this equation, because you can solve a lot from the complex power. We can manipulate it to solve for the impedance. And this is how we do it. So we know V is equal to I times Z. So we can replace V with that right there. And so therefore when you look at I and multiply times the conjugate of I, the angles cancel out, because you're going to have one angle that's negative and the same angle that's positive. When you add them together, they're going to cancel out. So pretty much you're left with just only the magnitude squared times Z. So therefore Z equals the complex power divided by the magnitude of the current squared. So there's a couple different methods I put down here that you can take to find the total impedance. All right, so it says since we're looking for the total impedance, we'll use the total complex power and the total current. So we can use that. Or we can use the source voltage divided by the total current. Or we can use this one right here, which is kind of weird the way it works out, but um, it reduces to Z, your impedance equal to the magnitude of your voltage squared divided by your complex power, and then you're going to take the conjugate of that, which all equals to 11.48 at an angle of 66.37 degrees ohms. More than likely, you'll be using this equation right here the most, but there may be some cases where you may have to use this one. Like, say, for example, if you know the voltage across a load and you know the complex power of that particular load, you can use this equation right here to solve for the impedance of that load. So it just all depends on what situation that you're in, what you're given, what you're not, will determine which equation would be most suitable for that situation. But majority of the time, you probably will be using this one right here, or this one right here. All right, so now let's find the total components of each load. So what I mean by the total components, I want to know what is inside this load right here. We know it consumes 150 watts, but what is it? it's going to be a resistive load because we don't have any inductive or reactive power, inductive or capacitive reactive power. So we know it's going to be a resistor, but what size resistor is it? And that's what we're going to find out. Same thing with load 2 and load 3. We want to know what size resistor and what size capacitor that's in this load right here. And what size resistor and what size inductor that is in this load right here. So let's do that. So let's solve for load 1. So to solve for load 1, so solve for the components of load 1, um, you're going to have to dig back deep and apply your knowledge of KCL and KVL and also your power formulas in order to do this. But for load 1, what do we know about load 1? Well, we know the total current that's flowing through load 1, right? We calculated that right here. 8.73 amps at an angle of 23.63. So therefore, we can go back to our complex power equation and solve for the impedance. And so for this particular case right here, because we know that load is purely resistive, we can substitute the S for the P, the complex power for our average power, and our impedance for our resistance. And so therefore your equation looks like this. R equals your average power divided by the magnitude of your current squared. So for example, so just to explain that one more time, whenever you're looking at this load right here, if I ask you what's the complex power of load 1, okay, well, the complex power load 1, we all know the complex power is a combination of your active power plus your reactive power. But in this particular case, we don't have any reactive power. All we have here is just our active power, which is 150 watts. So that's how we can substitute our P for S and Z for R, because our impedance is a combination of our real and imaginary components for a particular load. But in this case, we only have resistive loading. So therefore, it's just only going to equal to R. And so that's how we're able to substitute those variables in to solve for the resistive load of load 1. Now you can't do that if you have an inductor or capacitor in that load. Just only whenever you just only have a resistive load. So like for load 2, we couldn't do that. So for load 2, we're trying to find, let's go back up here. We're trying to find one or two things. Either we need to figure out the current that's flowing through load 2, or either the voltage that's across load 2 in order to find the impedance of it. And so we know the current that's flowing in this direction, and we can't really use a KCL to determine the current that's flowing in this direction and in this direction. But since we calculated the component that's in load 1, which is 1.97 ohms, what we can do at that point is use a KVL So we like we done down here. So as we calculate the voltage of load 1, we get 17.18 at an angle of 23.63 volts. And so therefore, if we do a KVL, we can take your source voltage minus your load voltage of your load 1 voltage to determine your voltage across load 2. And that's just a simple KVL. So we're taking source voltage minus this voltage, which should equal this voltage right here. Because we all know the sum of the voltage in a loop should equal 0. That's your standard Kirchhoff voltage law. All right, so let's go back down here. All right, so now we can manipulate we're going back to our complex power equation. We can use this equation to solve for the impedance. And so now that we know the voltage, we already know the complex power is given to us in the problem. We can calculate the impedance of load 2. Like so. And don't forget to take that conjugate. Oh, I added this note down here. So pretty much what I did, I like working in polar notation. So this value right here is just load 2 in polar notation. The complex power of load 2 in polar notation. So, like I said, this is optional, but this is why I like to work in polar. But the last thing you don't want to do is you don't want to forget to take that conjugate. Wait a second. So let's do a little checking on load 2. So load 2, we know load 2 is supposed to have a capacitive um, reactance. So therefore, we know that if in terms of the impedance, it's supposed to be negative. And so just like we saw right here, has a negative angle. And if we express this in polar, do I do in polar? Yeah. So I convert it to polar, it's still negative. So that's how we know we've done it correctly. So the resistive load of load 2 is 43.51 ohms, and the capacitive reactance load of load 2 is negative 34.81 ohms. And so we can actually figure out the actual value of that capacitor by manipulating our equation for reactance, capacitive reactance. So you get 1 over 2 pi FXC, which is your capacitive reactance. And so you just plug and chug. So 60 hertz that was given in the initial problem, which is the frequency. And so you get 76.20 microfarads. And so we can take the same approach for load 3. To figure out the inductive reactance. And so right here, we get our impedance for load 3 in polar notation. If we break it out into polar and into rectangular, we'll get our resistive and inductive reactance components separately broken out. And so if we use our inductive reactance formula manipulated to solve for the inductance, we'll get 26.10 millihenries. So like I said, this was kind of a long example, but it really touches on a lot of different pieces that can be used in your homework assignments. But what I want you to do, so if you replace the loads with its actual elements and components, the circuit will look like this. So what I encourage you to do is to reverse engineer this example and solve for the total impedance, current, and the complex loads to confirm your understanding in our analysis. So you already have the answers. We done already solved for them, and so let's see if you can reverse engineer this and derive the same thing. If you were given this circuit right here, so try to see if you can solve for the total impedance, the total current, and the complex power loads for each load. So load 1, load 2, load 3. And the complex power should equal the original problem right here. All right, so that leads into our next topic, which is the power triangle. So the power triangle is the representation of a right angle triangle showing the relationship between active power, reactive power, and apparent power. So if you have a lagging power factor, your power triangle will look like this, where you have your active power or average power, and then your reactive power, because it's inductive, will be going up because it's positive. And then of course the hypotenuse is your complex, is your apparent power. And the opposite for a leading power factor. So when leading power factor, your reactive power is negative, right? And so this angle right here, this is the angle of your network. And so and also the hypotenuse for this right triangle is your apparent power as well. So here's a few more equations. So it's a little bit of trigonometry, but it's not bad. So if you want to solve for your apparent power, which needs to have some vertical bars right here, apparent power, you can take the square root of your p squared plus q squared, your average power plus your average power squared plus your reactive power squared, and you can get your apparent power. All right, and the same thing if you know your angle, So the sine of theta is equal to the your reactive power divided by your your apparent power. Make this right. So this is pretty much the relationship, the equation that you would need to know in order to solve for one of the other values. So if you're given at least two of the four terms of a power triangle, you should be able to calculate any of the remaining terms. So like for example, if I gave you only your P and S, right? Your average power and your apparent power. You should be able to calculate your angle. You should be able to calculate your power factor, and you should be able to calculate your reactive power. So if you just know at least two of the four values of this power triangle, you should be able to solve it for the remaining values using one of these equations. I mean, you may have to do some manipulating of the equation, but you should be able to get it. And so here's an example. So if I gave you your real power or your average power, which is 5 kilowatts, and your reactive power, which is 1.5 kilovars, I want you to find the apparent power, the phase angle, and write the complex power in rectangular form. So, so we can use Pythagorean theorem to find our apparent power. We can also come up here and use one of these equations. So this one right here is it's a pretty popular one right here. The, the, the inverse cosine or the arc cosine of your average power divided by your apparent power will give you your angle. All right. And the complex power will just be I mean, you can calculate it, you can throw it into your calculator, but I mean you've already you have everything that you need right here in order to put the complex power in polar notation. So you have the magnitude right here, and also you have the angle. And then you can also convert it to rectangular. All right, so that's it for this part of module 7 lecture. If you have any questions or anything that you are unsure about, feel free to reach out to me. But that's going to conclude this lecture, this section of this lecture. Next part, we're going to talk about power factor correction. So I'll see you in the next video.